Greetings everyone. So today we are going to discuss about the new topic which is Group 7A Elements. Group 7A Elements also known as the halogens. Why do we call them halogens? Because they are salt producers. It is derived from the Greek word halo which means salt and gen or genesis which means the producer. They are literally the salt producers because these are from where most of the salt including the common salt is made and these include elements chlorine, bromine, iodine, and astatine. Astatine is more of a radioactive one. It's a radioactive metal, and its half life is something around 8.3 hours. While iodine is basically a gray blackish solid. Bromine is a reddish brown liquid. Chlorine is a greenish gas, and fluorine is a pale yellowish gas. So these are some common physical properties, and alongside that, they have certain common characteristics for which this group is famously known for. Number one characteristic is their electronegativity. Electronegativity. What is meant by electronegativity? The ability to pull the electron pair towards itself is electronegativity, and that is found greatest in the entire periodic table in fluorine, which is also taken as the arbitrary electronegativity value, which is 4.00. And if you just take uh, the trend of the electronegativity in halogens, electronegativity decreases down the group. It decreases down the group. Decreases down the group. Electronegativity is decreased. And why is that so? That is because of increased atomic size and higher shielding effect. Increased atomic size and increased shielding effect, due to which there is decreased electronegativity. And with that, the metallic characteristics, the stability, metal characters decrease down the group. Sorry, stability increases, metallic characteristics increases, and reactivity all right. Stability decreases, reactivity increases. So these are some of the general trends. And another important thing is that chlorine, bromine are used for organic reactions. In most of the organic reactions, we do not use fluorine because fluorine is very reactive, which can cause explosion, and iodine on the other hand side uh, is solid in form and is not that reactive to undergo reaction. So ideally, we use chlorine or bromine for organic reactions. All right. Now let's just move on to the peculiarity of fluorine. As I previously told that fluorine is the most electronegative element not only in the group 7a but in the entire periodic table. It has certain peculiarities. What are those peculiarities? Let's understand. Number one peculiarity is its high electronegativity value. It is highly electronegative. It is highly electronegative as well as it has a high ionization energy. High ionization energy. What does that mean? That means that it is having a high lattice energy, because lattice energy is the ability to uh, you know break apart its electron and dissolve in water, due to which there is high lattice energy, and that high lattice energy makes it unable or insoluble in water. Insoluble in water. Insoluble in water. Fluorine gas is insoluble in water, but hydrogen fluoride is soluble in water. Reason behind it is that hydrogen fluoride has hydrogen bonding. But fluorine gas does not have any sort of intermolecular forces, as a result of which the fluorine gas is insoluble in water. And it has got a very small size, because it has a high electronegativity value. It attracts the electrons so tightly that it's got a really small size and a high nuclear charge, of course. And then we have its low dissociation energy. Low dissociation energy. What does this mean? This means that whenever we are going to provide it even a small amount of energy, it can get reactive. It is highly reactive because of its low dissociation energy. So if you just, let's say I take fluorine and I just provide it with a little amount of energy. Let's say if I take fluorine gas and take hydrogen gas, and I'm not providing it even temperature, an increased temperature. I'm putting it at ordinary temperature. It will produce hydrogen fluoride at ordinary temperature. Without any source of energy, it will provide hydrogen fluoride. It's that reactive. And let's talk about point number 4, which is that it is inert. It is basically restricted. It has it is restricted restricted to octet shell, which means that whenever it forms a bond with certain compounds like carbon and sulfur, it restricts itself to the octet shell, due to which it becomes inert, such that carbon tetrafluoride or silicon, not silicon but sulfur hexafluoride, carbon tetrafluoride, they are inert. These are inert compounds which cannot react further. So it's restricted to octet shell, and which makes it pretty inert, and that's also the reason that its oxidation state is only -1. Other halogens such as chlorine, bromine, iodine, they have oxidation state as +1, +3, +5, +7, but fluorine is only having one oxidation state, which is -1. So uh, this is another point. And now the very last thing over here, which is that it can reaction with inert gases. Fluorine is the only element in the entire periodic table which can react with inert gases like krypton and xenon to form krypton fluoride and xenon fluoride. krypton fluoride and xenon fluoride. We are going to discuss that as well. So these are certain common characteristics. Now let's just move on to its oxidizing properties. That how is fluorine, how is fluorine or chlorine or bromine iodine can be used as oxidizing agents, as well as can be used as reducing agents. So there are certain general properties of a reducing agent. A reducing agent is supposed to have a reducing power. Reducing agent is supposed to have reducing power, which is hydrogen or proton. And an oxidizing agent is supposed to have oxidizing power, which is oxygen. So if if a halogen is having oxygen, if a halogen is having an oxygen, then it is in an oxidized state. Or even if a halogen is in its free state, then in its free state it will be it will possess if it is in its free state, then it has the capability to accept hydrogen and become reduced, and thus the in free state fluorine, chlorine, bromine and iodine are reducing agents. Now we just take the power of the reducing agents. Reducing agents have the odd strength of reducing power from fluorine to chlorine, bromine and iodine. And if you just take, by the way, um, halogens can act as oxidizing agents as well as they can act as reducing agents. The strength of order for both of them is reverse. Fluorine, bromine, bromine, iodine over here. When they are in free state, fluorine is the best reducing agent among all the halogens, and iodine is the best oxidizing agent among all the halogens. Oxidizing agent, reducing agent. And another important thing when it comes to reactivity, when we discuss in terms of reactivity, fluorine is the most reactive, after which iodine is the second reactive one, bromine on third position, and fourth position chlorine. That's it. And then there's an important fact. There is an important fact which needs to be considered over here, that a compound which contains chlorine or bromine or iodine can be easily displaced by fluorine in a chemical reaction. What I really mean by this is that, for example, if I take copper chloride, I take copper chloride and I react it with fluorine, then this reaction is possible to happen, such that copper will be the chlorine would be displaced and will produce copper fluoride plus chlorine. If bromine is reacted with iron, bromine is reacted with ferrous chloride, then will this reaction happen? this reaction will not happen. Why will it not happen? Because chlorine chlorine can displace bromine, but bromine cannot displace chlorine. That's a rule. Why is that rule? I'm going to tell the reason as well. But for now, let's just understand the reason. Understand um, the scenario over here. That whenever we are having whenever we are having a higher halogen atom, then it can displace chlorine from a compound, bromine from a compound, iodine from a compound. But a smaller halogen atom, which has basically smaller, not smaller, but basically a halogen atom which is you know less reactive, can not displace the higher halogen atom. Fluorine can displace chlorine, bromine, iodine. Chlorine can displace bromine and iodine, and bromine can displace only and only iodine, and iodine cannot displace anyone. But chlorine cannot displace fluorine, bromine cannot displace chlorine, iodine cannot displace all three of them. Now let's understand why does it happen. Why does this pattern follows? This pattern follows because of the atomic size. Because of the atomic size. It's simple. Fluorine has a very small atomic size. Fluorine has a very small atomic size, and that small atomic size uh, can actually attract electron towards it due to its high electronegativity and smaller atomic size, high electronegativity and smaller atomic size, due to which it can easily attract the electrons from chlorine as well as attract the electron pair from bromine and iodine. But if I am, let's say, having chlorine on the other hand side, chlorine is larger in size and has less electronegativity value than fluorine. At that point, chlorine cannot take away the electron pair which is being attracted by fluorine, because fluorine has an electronegativity of 4, chlorine has an electronegativity value of 3. So it's a huge difference, right? It cannot attract the electron from someone who has already a lot of power to hold that electron pair, due to which having less electronegativity value, it cannot take away the electrons of fluorine and cannot displace fluorine as a result. Same goes with bromine, same goes with iodine as well. Now let's move on to some chemical reactions. uh, we have three major compounds which are formed with halogens, which includes the hydrogen halides, oxyhalides, and oxyacids. Let's first understand hydrogen halides. Hydrogen halides are formed when hydrogen reacts with a halogen to form a hydrogen halide. Now, the reaction is not that simple. If it is in case of fluorine, the reaction can happen at ordinary temperature and pressure. But if the reaction is, let's say, with iodine, then it needs to be carried out at a particular temperature, a very very high temperature, at a very high pressure, something around 3 atmosphere and something around 200 centigrade. It's just an approximate temperature, not the actual temperature. And these hydrogen halides have basically the characteristics. Again, these hydrogen halides have a lot of different characteristics. For example, if you just take example of hydrogen fluoride, it is a very reactive acid. It is a very sorry. It is a very strongly bonded acid. Acid, strongly bonded acid, and it is a very stable acid, not a reactive acid, because reactive acid, most reactive one is hydrogen iodide. So hydrogen fluoride is that reactive that even if we just put it in a container of glass, it can dissolve the glass in it. So in order to avoid this condition, we actually preserve hydrogen fluoride in a stainless steel vessel, or a glass vessel kept in vacuum, or we add poly tetrafluoroethyl PTFE or Teflon, which basically decreases the reactivity of hydrogen fluoride so that we can store it in the glass. Polytetrafluoroethylene. It has formula as well. It's pretty long, something like this: CF3, sorry, CF2. It's basically CF2, and then two bonds here, CF2, two bonds here, and in that way, there's an entire polymeric chain, which is polytetrafluoroethylene, also known as Teflon. And when it comes to its reactivity, the strength of hydrogen halides. Nowadays, it is also found recently that hydrogen fluoride in gaseous form, in vaporous form, in liquid or vaporous form, hydrogen fluoride, sorry, in liquid form, it is stored in that way, and with Teflon, and in vapor form, it can exist in equilibrium with its monomeric form. It's a monomeric form, and in a cyclic hexamer, in a cyclic hexamer, in the state of vapor. And when it comes to its strength of hydrogen halide, we just compare all of their strength. Then we need to again understand the basic concept, which is that fluorine is highly electronegative, due to which it will attract the electrons of proton more towards it, due to which it is less likely to give its electron pair, due to which it is less likely to give its electron pair, due to which it will make a strong bond, due to which it will make a strong bond. Why? Because fluorine has a high electronegativity, hydrogen has less electronegativity, due to which the electronegativity difference is pretty high, which makes the bond pretty stronger. And secondly, we have on the contrary hydrogen iodide. Hydrogen iodide is having less electronegativity, so the bond electronegativity difference is pretty weak, due to which the bond is weak, a weak bond. As a result of this, hydrogen fluoride comparative to hydrogen iodide is less reactive and more stable, and that is more reactive. Of course, we cannot consider in terms of reactivity as a whole, because reactivity actually can be defined in a lot of terms. In terms of giving away the hydrogen atom, there is less reactivity of hydrogen fluoride, and in terms of giving away hydrogen atom, hydrogen iodide is having more reactivity. So in simple words, its strength would be hydrogen iodide, hydrogen bromide, hydrogen chloride, and hydrogen fluoride. This is a relative strength. And another important point to be considered here, which is that hydrogen fluoride is having bond interactions, has having physical forces of interactions as well. which is known as which is known as the hydrogen bonding. It is having hydrogen bonding in itself as well, and due to this, it is having a higher melting and boiling point as compared to all of the other halogens. Also, the trend of melting and boiling point is decreasing down the group, because when we go down the group, the melting and boiling point starts decreasing downwards due to less electronegativity. And other other halogens such as HCl or hydrogen bromide, they are having dipole dipole interactions. So this is basically all about it. Now let's understand what is the concept of oxyhalides. Here we are mostly going to study reactions, because oxides are have oxides of fluorine are pretty less, and we're going to study few of them. So basically, we are having oxides of fluorine such as oxide oxygen difluoride, dioxygen difluoride, trioxygen difluoride, and oxides of bromine such as bromine monoxide, bromine dioxide, bromine trioxide, um, oxides of chlorine, um, oxides of chlorine such as chlorine dioxide, chlorine pentoxide, chlorine heptoxide, and alongside that we are having iodine oxides as well, iodine dioxide, uh, iodine iodate, which is I4O9, I2O5, I4O5. All of these are salts. These are iodine oxides. These are basically in salt form, so these are named as iodine iodates. Anyways, let's come on to this point. Let's come to this point, which is first the trioxygen difluoride. So the trioxygen difluoride can be prepared when a mixture of fluorine and oxygen is subjected to electrical discharge at 363 centigrade. It is a dark red viscous liquid which turns to reddish brown solid at 350 centigrade, and basically on decomposition it gives dioxygen difluoride and oxygen molecule. And we are when trioxygen difluoride reacts with fluorine, it gives dioxygen difluoride as well. And when it comes to chlorine, it has some extensive use in bleaching agents as well. The famous bleaching powder, calcium hypochlorite, is basically having the chlorate group in is basically having chlorine dioxide in it. So it is basically a pale yellowish gas. It can be prepared by reducing sodium chlorate with sodium chloride or sulfur dioxide in a strongly acidic solution. And chlorine dioxide can be prepared by action of H2SO4 on potassium chlorate, and chlorate explodes into chlorine and oxygen on warming. It is soluble in water and is stable in tar. It decomposes slowly in H2O to HCl and uh, HClO3, and it is a paramagnetic substance. Can be used for purification of water, antiseptic, and bleach cellulose of material. Chlorine heptoxide basically is an anhydrate of perchloric acid, can be obtained at -10 centigrade, and by dehydration of perchloric acid with phosphorus pentoxide. Oxides of bromine are dark, volatile liquid with low thermal stability. It can be prepared by the reaction of bromine vapors with mercuric oxide. And bromine oxide can be prepared by treating the suspension of mercuric oxide in carbon tetrachloride. It is stable in dark carbon tetrachloride at -20 centigrade. It has oxidizing properties. Oxides of iodine. It can be prepared by heating iodic acid at 240 centigrade. When we heat iodic acid at 240 centigrade, we get iodine pentoxide, which is a white crystalline solid, stable up to 300 centigrade, and has a polymeric structure and is insoluble in organic solvents. It forms iodic acid with water. and it reacts with hydrogen sulfide, hydrogen chloride, and carbon monoxide to produce carbon dioxide and iodine. Also used for analysis, quantitative analysis of carbon monoxide. And alongside that, there's an interesting thing about when we react sodium hydroxide with when we react sodium hydroxide with fluorine, chlorine, or bromine or iodine. When we react with them with halogens. For suppose, let's say if I take sodium hydroxide and let's say I take sodium hydroxide and I react it with I take sodium hydroxide and I react it with let's say chlorine at minus 10 centigrade. The product which I'm going to get is HCl, hypochlorous acid, HCl, hypochlorous acid, and sodium chloride. This is the product which I would get. Now, if you just see in this reaction, the oxidation state of chlorine here is 0. In HCl, its oxidation state is -1. In hypochlorous acid, it is having its oxidation state as +1. So you might see a difference that when this reaction happened, the oxidation state changed to -1 as well as it changed to +1. So because of because of the of a particular compound being both oxidized as well as being reduced, a particular compound being oxidized as well as being reduced in the same reaction, this type of reaction would be named as disproportionate reaction. I'm not sure about the actual spell, but disproportionate reaction. Alright. And another interesting thing, this is not the final product. This is not the final product. The final product is when HOCl, hypochlorous acid, further decomposes into chlorine gas and hypo it further decomposes into chlorine gas and hypochlorous. So this is about it. Alright, let's just move on to the next part, which is the oxy acids. Now, when it comes to um, chlorine, bromine, and iodine, chlorine, bromine, iodine, all of these form oxy acids because they are not restricted to a particular oxidation state. But fluorine does not form oxy acids. It hardly forms hydroxyfluoride, but that is also an unstable state and also an intermediate state which does not exist in environment for a very long time. So in general, it does not form oxy acids. Fluorine, bromine, iodine form oxy acids. Now let's just understand the oxy acids through this table. If you just see oxy acids which are created with +1 oxidation state, which that includes the hypochlorous acid, hypobromous acid, hypoiodous acid. with plus 3 oxidation state, it's Helles chlorous acid only. It does bromine and iodine do not form the Helles acid. With plus 5 oxidation state, there is chloric acid, bromic acid, and iodic acid. And with plus 7 oxidation state, there is only iodic acid, periodic acid, and perchloric acid. Now, you might be confused about the nomenclature that might have been bothering you. So let's just understand the nomenclature as well. Whenever we are going to have, this is an oxy acid. This is an oxy acid of halogen. Whenever an oxy acid of halogen is having one oxygen atom, when oxy when oxy acid of halogen is having one oxygen atom, the oxidation state of halogen is plus 1, and at that point the acid is said to be hypohallous. In place of hallous we will write the actual in the place of hell we will write the name of the particular halogen. For example, if it is chlorine, then we write chlorus. If it is bromine, bromus. Iodine, iodus. In this case I am just generally writing hypohallous. This is the keyword to remember: hypo and us. These are the keywords to be remembered. And acid. And when a salt will be produced of this acid, that would be named as hypo, and then hell would be replaced and ITE. This is the thing. This is the first part. Second part, if we are having two oxygen atoms, let's say two oxygen atoms, then at that point the oxidation state of halogens would be plus 3, and when the oxidation state would be plus 3, it would be named as Hallous acid, and the salt would be called as halite. Now, another important thing, when there are three oxygen atoms, we just see, when there are three oxygen atoms, if there are three oxygen atoms, then at that point if there are three oxygen atoms, then the valency would be plus 5. Sorry, not it's not a valency, it's oxidation state. The oxidation state would be plus 5. Valency does not have positive negative signs, so oxidation state would be plus 5, and at that point it would be named as halic acid. For example, bromic acid, chloric acid, iodic acid, and its salt would be named as ATE salt, halate salt, ATE salt, halate. And on the contrary, if we are having, let's say, four oxygen atoms, then at that point, when there are four oxygen atoms, there would be plus 7 oxidation state, and this would be named as perhalic acid. Perhalic acid. That perhalic acid will form a salt which is perhalate. Yes. So this is all about the nomenclature of oxy acids, and when it comes to the a study of um, oxy acids. We are having the most famous oxy acid, which is known as the perchlorate. Oxy acid, which is perchlorate, perchloric acid, which forms the salt perchlorate. There are certain characteristics, certain points to remember about it. It is basically used as an antiseptic. It is used for making insecticides, for purification of water, and for bleaching. It is important to understand that it is soluble in aqueous solution. It is only available in aqueous solution. Whenever we are going to utilize HClO4, we are only going to use it in aqueous solution, and within aqueous solution it should be 67% solution in water, because if we are going to use more than that, or the pure form of chloric perchloric acid, then it's going to blast, and it's the strongest acid in an aqueous solution. Strongest acid in an aqueous solution. Another important point to remember in this case is that it can be prepared by reaction of potassium chlorate with concentrated H2SO4. At that point, we will get perchloric acid with potassium sulfate. So this is an important point. And perchloric acid is also used for as an oxidizing agent. It is basically a strong acid. It is a strong acid, and it is also used as an oxidizing agent. It is used as an oxidizing agent. For example, if you are going to, if you want to if you want to, oxidize, um, uh, let's say if you want to oxidize, if you want to oxidize hydrogen sulfide, if you want to oxidize hydrogen fluoride, then it's going to, oxidize, work as an oxidizing agent as well. And um, perchloric acid is also, when it is dissolved in water, it produces chlorate ions. It produces chlorate ions. When it dissolves in water, it produces chlorate ions. And hydronium ions. Alright. And apart from that, there is a trend in the reactivity of the oxy acids as well that we need to understand. Here, this trend is this, that oxy acids which are having four oxygen atoms, oxy acids having four oxygen atoms, four oxygen atoms are more strengthful, have more acidic strength. Let me just write it over here as well, that the acidic strength, thermal stability, acidic strength or thermal stability is in such a manner that perchloric acid has the highest acidic strength and thermal stability. Then we have the halic acid. Then we have the Hallus acid, and then we have the hypohallus acid. This is the trend of acidic strength and thermal stability. Why does it happen? Because when there are more number of oxygen atoms, there is more electronegativity to attract the electron pairs towards itself, due to which it is easier for the proton to be left it is easier to attract the electron pair towards the oxygen and you know throw the proton away in the aqueous solution, due to which the solution becomes more acidic when there are more number of oxygen atoms in the solution. Likewise, when there is more electronegativity, more electron pairs are holded tightly within the perchloric acid or perhalic acid, due to which the thermal stability is ultimately increased. And with that, the oxidizing power, the oxidizing strength is also increased uh, from perhalic acid to halic acid to Hallus acid to hypohallus acid. So these are certain points about the oxy acids. Now let's just move on to our final topic, which is bleaching powder. Bleaching powder, also known as calcium hypochlorite. Calcium hypochlorite. It is a calcium salt of chlorous acid. Calcium salt of chlorous hypochlorous acid. Hypochlorous acid. And that is basically commercially prepared with the by passing chlorine gas on dry slaked lime. How do we do that? There are two methods. One method is the Hessen-Clever method, in which the Hessen-Clever plant is used. This is the old method, in which basically there are 4 to 8 rectangular. There are 4 to 8 iron cylinders, which are horizontally arranged and connected to each other with stirrers. And alongside that, on the top of that, we have a hotter or hopper. I'm not sure about the actual word, but that's the opening from where the slaked lime comes in. Dry slaked lime powder comes in, and that is basically the stirrer which are present in each of the iron cylinder is stirred, due to which the dry slaked lime is able to move from one cylinder to another cylinder, finally to the lowest cylinder where the chlorine gas is poured. Lowest cylinder in which the chlorine gas is present, where the chlorine gas reacts with the slaked lime in order to produce calcium hypochlorite, which is collected from the outlet. Now, some drawbacks of this plant is that a lot of chlorine gas molecules are present in the lowest cylinder, due to which uh, the chlorine gas, by the time slaked lime reaches the lowest cylinder, is lost or is diffused into the air, due to which a lot of economic loss happens. Likewise, during this reaction, um, it is required that there should be a catalyst, or a bit of hot temperature should be there. If there is no hot temperature, it basically it tends to be ineffective, and some of the chlorine molecules react with um, do not react with slaked lime to produce calcium hypochlorite. So a better version of this was given by Bachmann's method, and that basically again involves the exact same material. There are 8 iron cylinders, but instead of being arranged horizontally, they are arranged in a tower vertically. If you just see, these cylinders are arranged vertically, and each of the cylinder is basically having a rotor. This is a rotor such that when we turn on the machine, the slake line which is coming from the hotter slake line which is coming from here in compressed air, is rotated continuously with the help of the rotor, so that the chlorine gas which is present in the entire tower is easily mixed with slate line. So basically, chlorine gas is entered from this side, from the lower cylinder, and slate line from upper cylinder. Alongside that, hot air is also inserted from the lower cylinder. Both of these mix together by rotating the rotor, as a result of which both of these mix together and produce the bleaching powder, calcium hypochlorite, which is collected from the outlet. And that procedure is pretty effective because there's an involvement of rotor, as well as there's involvement of hot air, which was not present in the previous technology. So now let's understand its benefits. It is an oxidizing agent, such that it can produce hypochlorite ions and just undergo cause oxidation. It also gives hypochlorous acid when reacts with dilute sulfuric acid. And if there's an excess of an acid, then it can produce chlorine gas. For example, if there's excess of sulfuric acid, it can produce chlorine gas. And at that point, when that chlorine gas is produced, this is known as the available chlorine or free chlorine. That available chlorine or free chlorine basically determines the amount of oxidizing capability of the bleaching powder. If there's more chlorine gas available, if there's more available chlorine gas emitted out, it means that there is more oxidizing capability, oxidizing power of the calcium hypochlorite. Usually, the calcium hypochlorite has the capability of 35 to 40%, and it has an oxidizing capability. It can oxidize hydrogen chloride, hydrogen bromide, hydrogen iodide to their halogens. It can oxidize ammonia to nitrogen, and it can even react with carbon dioxide to produce calcium carbonate. So in that way, these are certain reactions which were important. Now let's just understand few commercial uses of halogens. Halogens have been pretty useful. For example, if we talk about fluorine, fluorine is useful for preparing uh, freons. Freons is are low molecular mass chlorofluorocarbons, which involves examples of carbon dichloride, difluoride, carbon monochloride, trifluoride. All of these are examples of low molecular mass chlorofluorocarbons, which can act as refrigerants and aerosol propellants. And alongside that, we have polytetrafluoroethylene, which is used for storing acids, alkalis, and halides, hydrogen halides, and they can be used for creating corrosion-free machinery parts, corrosion-free parts of machine. They can be used for of uh, coating of electrical wires, as well as they can be used for creating non-sticky creating the non-sticky coating of cooking pan, non-sticky coating of cooking pan. They can be used for creating non-sticky coating of cooking pan, so creating corrosion-free parts of the machine. And it can be also be used to create disinfectants and water treatment plants, and it can also be used for storing acid, alkalis, and halides. Another important thing that needs to be considered over here is that we have halothane, a special compound known as halothane. What is halothane? The structure of halothane is like this. It's basically three fluorine atoms attached to one carbon, and the other carbon having chlorine, bromine, and hydrogen. This structure is known as halothane. Now, this halothane is of particular importance because uh, it is used as an antiseptic, not antiseptic but as an anesthetic. It is used as an anesthetic. So this is an important thing. And we have chlorine. Chlorine is the most famous one. It is used for the manufacture of chlorofluoro. It is used for the manufacture of chloroform, for formation of tetrachloromethane. It is used for the formation of chloroform, tetrachloromethane. Used for making bleaching powder. It is used for making HCl, which is the cheapest acid. It is used for making polyvinyl chloride. It is used for making PVC. It is used for making antiseptics or insecticides, herbicides, herbicides, insecticides, herbicides, insecticides, and for making HCl, calcium hypochlorite, for making chloroform, for making carbon tetrachloromethane, for making PVC, for making it can be used as a disinfectant. And in that way these are certain uses. Now when it comes to bromine, bromine is again of particular importance. It can be used to make insecticides, particularly it can be used to make fungicides. Silver bromide is used in photography, basically in X-ray photography and other types of photography. We have this silver bromide utilized. And apart from silver bromide, there is this bromine gas, silver bromide, and we have a compound known as ethylene bromide. Ethylene bromide. This ethylene bromide has a capability. We basically use ethylene bromide in gasol in the engine because um, it mixes with the lead containing gasoline to make the engine free from lead, such that dibromide prevents the action of several leaded compounds in gasoline, such as lead sulfate and lead oxide, to damage the engine. So it prevents the damage of engine by inhibiting the action of lead oxide and lead sulfate in the leaded gasoline. And how does that lead come? That comes from tetraethyl lead, TEL, tetraethyl lead. That tetraethyl lead is again a different topic which we have studied in cracking and reforming. So these are few more advantages. Apart from that, we have iodine. Iodine. Iodine is itself, important for the human body because it is used for normal metabolism. We basically take iodized salt, which is basically salt containing minerals such as potassium iodide, sodium iodide, so that that can be provide used for normal metabolism of the body. And if it is not present, then it can cause a condition known as goiter. And another important thing is it it is popular. It has some popular preparation which is known as tincture iodine and iodex. Tincture iodine and iodex, alongside which iodine is also famous for its tincture iodine and iodex, and alongside that it is famous for its pharmaceutical uses, such that it is used as a germicide and as a disinfectant. So that's all about it. So hopefully you enjoyed this video. Hopefully we'll meet again in another video.